Hello students, welcome back. So in this lecture we'll start with the properties of DFT, this discrete Fourier transform. The first property is periodicity. We have already proved the periodicity of DFT in the previous lectures, so I will not be proving it here again. I will be just writing it. So we know that x cap n corresponds to xk, this is endpoint DFT. Okay, so the signal is also periodic with period capital N and it is discrete, and the endpoint DFT, that is xk, is also periodic with period capital N and it is also discrete. So both are periodic with period capital N. Okay. Second property, that is linearity. Linearity means if we have two sequences x1n and x2n and we are finding endpoint DFT of both x1n let it is x1k and endpoint DFT of x2n and let it is x2k. So if I write the formulas, then it will be summation 0 to capital N minus 1, summation is on n, x1n e to power minus j 2 pi by capital N nk. Similarly, the formula for this will be okay. Now if I create a new signal, that is yn, that is a times x1n plus b times x2n, then the endpoint DFT of yn, that is yk, will be summation okay. And we can easily see that this is actually equal to a times x1k plus b times x2k. So we can say that DFT is a linear function, right? So this is actually following the superposition theorem. Okay, I hope you all know the superposition theorem. Okay, so the third property, that is time reversal property. For example, if it is given that xn has endpoint DFT, that is capital XK, then you have to find the endpoint DFT of x of minus 1, x of minus n. Okay, so we know that xk is equals to summation xn n equals to 0 to n minus 1 e to a minus j 2 pi by n nk. Okay, so this is your capital XK. Now let us assume that now we can see that let x of minus n has endpoint DFT, that is yk. So yk will be equal to summation n equals to 0 to n minus 1 x of minus n e to the minus j 2 pi by n nk. Okay, so if I replace this minus n by capital M for by m, let us say, so I replace minus n by a variable that is m, so it will be equal to x of m e to the power plus j 2 pi by n m k, and the summation will be still over a period itself, right? So it will be m equals to 0 to minus n plus 1. Okay, still this is the summation over a period, because we know that we have to do summation over a period itself, so still the summation will be over a period only, so this summation will be similar. Now this is your yk. Now this is your equation number 1 and this is your equation number 2. Now if you compare equation number 1 and 2, these two summations are exactly similar because they both are summation over a period. There's only a difference that you can see that here we have a minus sign in the exponential and here we do not have any minus sign. Okay, so modifying equation number 2, I can say that y of minus k is equal to summation m equals to 0 to minus n plus 1 xm, and if we replace k by minus k, so there will be a minus sign in the exponential. Okay, so this is equation number 3. So from equation number 3 and equation number 1, I can say that both are equal. So xk is equal to y of minus k, or I can say that x of minus k is equal to y of k. Okay, so it is yk that is equals to x of minus k. So simply I can say that if xn has a DFT of capital Xk, then x of minus n will have a DFT of x of minus k. Okay, fine. Now one more very important thing that I would like to tell you here, it's that suppose this is your xn, so here it is x0, here it is x1, here it is x2, and let us say that n is equals to 7. Okay, so here it is x3 and so on. Finally we have x6, and okay, now since this is one period from x0 to x6, it will be repeated again and again. So here also it will be repeated. Okay, so this term will be x6, this term will be x5, this term will be x4, this term will be x3, this will be x2, and this will be x1. Fine. So here also it will be like this, and here also it is like this. Now if you draw x of minus n, that is time reversal, so these green terms will come here and these red terms will go to the left. So if you draw, then x0 will remain at the same location, so x0 will remain at x0, x6 will come at the location of x1, so this will be x6, this will be x5, x4, x3, x2 and x1, and then again it will be x0, x6, x5, x4 and so on. Okay, now if you look at one period of x minus n, okay, 0, 1, 2, 3, 4, 5, 6. Okay, if you look at one period of x of minus n, then you can say that look at x of minus n, then you can say that at n equal to 0 it is x0, at n equal to 6 it is at n equal to 1 it is x6, at n equal to 2 it is x5, at n equal to 3 it is x4. So x of minus n is actually defined as x of capital N minus n, or in this case it is x of capital 7 minus n. Remember this. Okay, because if you see that when n is 0 it is x of 7, and we know x of 7 is equals to x of 0 because it's periodic, xn is periodic. Okay, so remember this, a very important point. Similarly, we can say that capital capital X minus k is equal to capital X n minus k, that is capital X 7 minus k in this case. Remember this. Okay, so if in any question it is written that in case it is written x of capital N minus n, then you should understand that it is actually equal to x of minus n. Okay, so this is very important. Now since we know that x of n, if x of n has a DFT of x of k, then x of minus n will have a DFT of x of minus k, right? We have seen that. So if we have a signal, okay, in place of this I can write x of n minus n will have DFT x of n minus k. Okay, okay, now suppose we have a signal which is x of n is equal to x of minus n, or x of n is equal to x of capital N minus n. Okay, that is signal is even. Okay, so if any of this thing is written, okay, then it means the signal is even. Now when the signal is even, then we can say that the endpoint DFT will also follow this property, x of k is equals to x of minus k, or I can say that x of k is equals to x of n minus k, that is DFT will also be even. Okay, so for an even signal the DFT is also even, right? And similarly we can prove that, so for an even signal has even DFT, or for an odd signal has odd DFT. Okay, so this is very important conclusion that we can take from the above derivation or above property. Okay, so remember this. Now let's move to another property. I think it will be property number 4. Yes. Property number 4, that is circular frequency shift. Circular frequency shift, that is, if we have xn which has an endpoint DFT, that is xk, then okay, so whenever I write endpoint DFT, that means that the left side signal and the right side signal both are periodic with period capital N. Okay, even if I am not writing x cap n, then also it is true. Okay, so every time if I am not writing x cap n, then it means that the signal which is being written in the left side is periodic with period capital N. Okay, so xk minus L will be the endpoint DFT of which signal. Okay, so this we have to find. A very simple derivation, that is, we know that xk is equals to summation n equals to 0 to n minus 1 xn e to power minus j 2 pi by n n k. Okay, so this is the formula of DFT. This formula says that in the left side we have a DFT, endpoint DFT. In the right side we have a summation. Then we have the signal. To which this endpoint DFT corresponds, and then we have the exponential term, that is general term. Okay, so if this is a very important general format, so general format of the formula. So what is the general format of the formula? That is, in the left side we have the endpoint DFT of signal. Then we have the summation term. Then we have the signal itself to which the endpoint DFT corresponds. Okay, and then we have the exponential term. Now, if in this equation number 1, we replace k by k minus L. So x of k minus L. So in the whole equation, k will be replaced by k minus L. Okay, so very simple. Okay, okay. Now, if we this equation number 2. Now, if we compare this equation number 2 with this general format is very important. You can learn it. Okay. Okay. So, if we compare this equation number 2 with the general format, I can say that this is the endpoint DFT of this signal. Okay. So, xn e to power plus j 2 pi by n nl will corresponds to a signal which will have a DFT of xk minus L. Okay, so you can remember this. And generally, if you have all seen the properties of frequency shifting and time shifting of continuous time Fourier transform, Fourier series or DTFT, then you have always observed that the effect of the frequency shifting goes with the opposite sign. Okay, goes with the opposite sign. That is, here we are actually subtracting L, that is K minus L. So there's a minus sign here, but the effect will go with the positive sign. So you have observed this in all the other transforms. Okay, so this is the property of the frequency shifting. Okay, okay, circular frequency shift. Now, next property, time shifting property. Okay, so we have xn whose endpoint DFT is xk. We have to find the endpoint DFT of xn minus m. So this is the question mark. Okay, so we will be following the formula, that is, we know that xn is equals to summation k equals to 0 to n minus 1 upon n xk e to power plus j 2 pi by n nk. And if we write the general formula of the general format, we can say that on the left side we have a signal, on the right side we have 1 upon capital N, k equal to 0 to n minus 1. This is the DFT, endpoint DFT of signal. Okay, so this is the endpoint DFT of signal. So in the right side we have endpoint DFT of signal, in the left side we have the signal itself. Okay, so now that this is equation number 1. Now in equation number 1, if I replace n by n minus m, so I will get x of n minus m is equal to summation 1 upon n x of k e to power plus j 2 pi by n minus m k. Okay, so this can be written as 1 upon n. So these derivations, why I'm doing it, because sometimes the gate actually go into the depth of the derivations itself and ask the question from the derivations also. So just knowing the property can help you solving the easier questions, but if you know the derivations, then it will be very beneficial for you. It might take some time, but it will be very beneficial for you. And generally in all the classes they don't go through the derivations, they just tell you the properties. Okay, so here we can see that this is the result. So if you compare with the general format, then you will get that this is the signal and its endpoint DFT is this. Okay, so okay, so you can see that the effect always goes with the opposite sign. In time shifting, the effect goes with the same sign. Sorry. The effect goes with the same sign. That is, here also we have a minus m, and here also we have minus m. Okay, so in time shifting, the effect goes with the same sign. In frequency shifting, the effect goes with the opposite sign. So you can learn this. Okay. Now let's look at another property. So it will be property number 6. Complex conjugate property. That is, if xn has a n-point DFT, then x conjugate n will have n-point DFT. What will be the n-point DFT of x conjugate n? So now let's look at, now let us assume that yk is the n-point DFT of x conjugate n. So what will be the formula? First of all, in this equation, let me write xk. So xk is equal to summation n equals to 0 to capital N minus 1 xn e to the minus j 2 pi by n nk. Okay, so yk will be n equals to 0 to capital N minus 1, because we know the formula is the n point. Okay, let me write the formula first, general formula. So it's the n point DFT is equal to summation 0. We have already written this, right? So using this, I can say that n point DFT is actually, let us say it is yk, and the signal here will be x conjugate n this is equation number 2, this is equation number 1. Now we have to find the relationship between yk and xk. So still the equation number 1 and 2 are not same. So first of all, let's conjugate both sides in equation number 2. So when we conjugate both sides, so we'll be conjugating both sides in equation number 2. Okay, so we'll get y conjugate k is equal to summation n equals to 0 to n minus 1 xn e to power plus j 2 pi by n nk. So this is equation number 3. Now still equation number 1 and 3 are not same in the right side. So we will replace k by minus k in equation number 3. We have y conjugate minus k is equal to n equal to 0 to n minus 1 this is equation number 4. So we replace by k by minus k in equation number 3 and we get equation number 4. Now in equation number 4 and 1 we can say that the right hand sides are equal. So so I can say that y conjugate minus k is equal to xk. Now, or from here I can say that yk equal to x conjugate minus k, right? Easily we can see that. So the n point DFT of x conjugate n is x conjugate minus k. Okay, so you can remember this, or it can be written like this also. It is actually equal to x conjugate n minus k. Okay, we have already seen the transformation. What is it? Okay, so using this property, that is, if xn has n point DFT of xk, then x conjugate n will have n point DFT of x conjugate k. Okay, now using this x conjugate minus k, sorry. Now using this property, we can say that if xn is real, okay, we can write this also, this as x conjugate n minus k, right? Now, if xn is real, then xn equals to x conjugate n, because when signal is real, then it is equal to its conjugate, we know that. So, xk will be equals to x conjugate minus k, or it is equals to x conjugate n minus k, right? Now this is, we know that we have seen this earlier also, this property, that this is actually equal to, or it shows that xk is conjugate symmetric. Okay, so you have already studied all the properties of all the transforms, and you have already studied that when signal is real, then its transform is conjugate symmetric. So this property is valid here also, that when signal is real, then its DFT, endpoint DFT will be conjugate symmetric. And so we can say that xk equals to x conjugate, sorry, x conjugate minus k, or it is equals to x conjugate n minus k. It's the same thing. So it is conjugate symmetric, right? We also know that when any signal is conjugate symmetric, then its real part is even and imaginary part is odd. Okay, so we can say that the real part of xk will be even and imaginary part of xk will be odd. Okay, so these are actually the properties of conjugate symmetric. I hope you all know this. I'm not proving it, and I will be making another video for conjugate symmetric signals if required. Okay, so now also we know that conjugate symmetric signals also have the property that magnitude of xk will be even and phase of xk will be odd. Okay, so you remember this. So these are actually the properties. So if I just mark the properties of conjugate symmetric, so these are actually the properties of conjugate symmetric signals. Okay, these four are the properties. Okay, now another very important from the above derivation, we can say that above property, we can say that if the signal xn is imaginary, so in that case xn will be equals to minus times of x conjugate n, because signal is imaginary, so it will be minus times of its conjugate. So here xk will be equals to minus times of x conjugate minus k. So when the signal is imaginary, when xn is imaginary, so this actually proves that the DFT will be conjugate antisymmetric. When xn is imaginary, then DFT will be conjugate antisymmetric. Okay, so these are the properties. So we have seen, if I write a conclusion here, a very important conclusion. So we have seen that when signal is real, the DFT will be conjugate symmetric. When it is imaginary, then it is conjugate antisymmetric. When xn is even, then xk is also even. When xn is odd, then xk is also odd. So these four properties we have already seen. Okay, now another very important property that is there, let us see that. Suppose, so this is also a conclusion. Suppose xn is real, okay, and we know that xn corresponds to, has endpoint DFT, that is xk. Okay, now very important conclusion. So let us say that we all know that xn can be written as xn plus x minus n divided by 2 plus xn minus x of minus n divided by 2. So we know that this is actually the even part of xn and this is the odd part of xn. Okay, now if I take DFT of the whole equation, okay, so I take the DFT of the whole equation. So it is the xn has DFT xk. So this has a DFT, xn has DFT xk, x minus n has DFT x of minus k divided by 2. So we can say that this is the DFT of the even part of xn. Similarly, for odd part of xn, xk minus x minus k divided by 2. Now, since xn was real, so xk was conjugate, symmetric, okay, or I can say that x of minus k is equals to xk conjugate. Now putting this in the equation number 1. So for example, this is equation number 2. So putting equation number 2 in equation number 1, we can say that xk is equal to xk plus xk conjugate divided by 2 plus xk minus xk conjugate divided by 2. Now a very important conclusion. So we know that this part is actually the, okay, so we can say that so this is actually the DFT of even part of xn. So we can say that even part of xn has DFT, that is xk plus xk conjugate divided by 2. Okay, is it visible? Yeah. Okay, so and what is this actually equal to? Whenever we add a conjugate of itself, then we get, and divide by 2, then we get a real part of the signal, that is this will be equal to real part of xk, or we can say that even part of xn has endpoint DFT equal to real part of xk. Similarly, we can say that odd part of xn will have endpoint DFT, that is equals to xk minus xk conjugate divided by 2, that is actually equal to imaginary part of xk. Okay, so is this okay? So this is a very important conclusion, right? So whenever xn is real, even part of xn will correspond to the real part of xk. So a question can be easily asked that, for example, if any question xn is given and xk is also given to us, okay, and in the question we have to find the endpoint DFT of the even part of xn, so directly you can write the real part of xk as the answer. Okay, so this can be a tricky question for those who do not know this, and they will be actually solving it again, and if you know this, then you can directly get the solution. Okay, so a 2-marker question in GATE or any other exam can be done very easily like this. Okay, so let us continue with the conclusions. So I will copy the conclusions from here and I will add a few points here. Okay. Okay. Now, suppose, let us say that signal is real plus even. Okay, signal is real plus even. So xk will be conjugate symmetric plus even. Okay, so you can see that when it is real, xk is conjugate symmetric. When the signal is even, xk is even. So I am just combining the two. Cs is conjugate symmetric and even. So when xk is even, so it is equals to xk equals to x minus k, and when it is conjugate symmetric, it is xk is equals to x minus k conjugate. So this is equation number 1, this is equation number 2. Now if, so this is actually showing that xk is even, this is showing that xk is conjugate symmetric. Now from equation number 1 and 2, I can say that, from equation number 2, if I modify, then I can say that x minus k is equals to xk conjugate. This is equation number 3. So from equation number 3 and 1, I can say that xk is equals to xk conjugate. Okay, so when any signal is equals to its conjugate, then the signal is real. So I can say that conjugate symmetric plus even means that it is real plus even. Okay, so easily I can prove that when xn is real plus even, then xk is real plus even. So this is the proof of it. Now another derivation that you can easily derive is real plus odd signal will have the DFT equal to odd plus imaginary. You can prove it like this. I have done the proof here, so you can easily prove this also. Similarly, when it is imaginary plus even, then it is even plus imaginary. When it is imaginary plus odd, then it is real plus odd. Okay, so just prove all this. You can easily prove all this. You as I have proved this, you can easily prove all these 4. Okay, right? Now let's move on to another property. So what's the property number? Let's look at the number. The property number will be 7 now. Okay, so let's move on to the property number 7, that is multiplication of two sequences. So now let's look at multiplication of two sequences. For example, I have two sequences x1n which has n point DFT x1k okay, and this x1k will be thus equal to n equal to 0 to capital N minus 1 x1n e to power minus j 2 pi by n nk, right? Similarly, x2n has n point DFT x2k n equals to 0 to n minus 1 x2n e to power minus j 2 pi by n nk, right? Now suppose a new signal yn is created that is equals to x1n multiplied by x2n, then what is the DFT of that? Now since the formula of DFT will be, for example, let us assume that yk is a DFT and n equals to 0 to n minus 1 x1n into x2n e to power minus j 2 pi by n nk. This will be the formula, right? Now okay, so now in equation number 3 I will replace x1n in terms of x1m. Okay, so I have replaced, since we know that x1n has endpoint DFT x1k, but I am replacing k variable by m because in equation number 3 already we have a k variable, right? So we know that x1n is equal to 1 upon capital N summation x1m, summation is over m, e to power plus j 2 pi by n n m. Okay, now putting this in equation number 3, we can say that yk is equals to 1 upon n. There are two summations. One is m equals to 0 to n minus 1. One is n equal to 0 to n minus 1. x1m, x2n, okay, right? Now if I keep all the n variable terms having n variables together, okay, now if you look at this term and compare with equation number 2, then you can easily say that this term is actually equal to x2k minus m. So this is equation number 2. If I just see, so here we have k, so that's why we have k here also, but in this equation we have k minus m, so I will replace x k by k minus m in this equation number 2 and I will get this term. Okay, so yk is equal to 1 upon n summation over one period. Okay, now since both the terms or both the functions x1k and x2k were having a period of capital N, so this expression is called periodic convolution. Okay, okay, if you don't know the periodic convolution, then there is a video on this channel, Edamigo channel, on periodic convolution. You can go through that. Okay, so I will be not explaining the periodic convolution in this video, so there is a separate video, you can go through that for more clarity. Okay, so this is the formula of periodic convolution. I can just tell you that whenever two signals of same period are convolved, then normal convolution is not done, rather a periodic convolution is done, and periodic convolution formula is 1 upon n summation over one period and this expression. This is the mathematical expression of convolution. I think you all know that. In convolution, we have summation over an infinite region, that is from minus infinity to infinity. But in periodic convolution, we have summation over only one period. Okay. So this is the sorry. So this is the expression of periodic convolution. Okay. This is the expression of periodic convolution. Only this, not 1 by n. 1 by n is not part of periodic convolution. Okay, 1 by n is not part of periodic convolution. This is the periodic convolution of two signals x1k and x2k. Okay, so yk is this, and this is the periodic convolution of two signals. So I can say that yk is equal to 1 upon capital N periodic convolution of two signals. Periodic convolution is represented by this symbol as I have written here. Okay, so this is the periodic convolution that has expression equals to this. Okay, summation over a period, and this is the expression of the convolution that we all know. Okay, so this proves The seventh property, that is multiplication of two sequences, multiplication in time domain is convolution in frequency domain, that we all know. But since DFT has periodic signals, that is x1k and x2k, so the convolution will be periodic convolution. Now let's move on to another property, that is property number 8. Sorry. Periodic convolution of two signals. Suppose x1n has endpoint DFT x1k, x2n has endpoint DFT x2k. So x1n periodic convolution x2n, because we know that these two signals are also periodic with period capital N. In case of DFT, it's there. The signals are also periodic. So then what will be the DFT? Okay. So let us assume that. Okay, so just go through the video of periodic convolution, things will be very much clear. And from that video you will also know that whenever we convolve, whenever we periodic convolve two signals having period of capital N in this case, then the result will also be periodic with period capital N. Okay, so yn will also be periodic with period capital N, and the expression will be summation over one period. Okay, so let us say that yk is the DFT of yn, so this will be the expression. Okay, now we replace yn by equation number 1. Okay, so this is equation number 2. Now if I club all the variables which has n, then in this equation, then this equation will be okay, so this is x1m will be outside, x2 n minus m. Okay, now this I can say that this is actually DFT, endpoint DFT of x2 n minus m, and we know the time shifting property, the effect goes with the same sign, so it is DFT, it is DFT of x2 n minus m. So this summation can be written as x2k e to power, effect goes with the same sign, 2 pi by n m k. Okay, now if I club all the terms which are of m, so this can be written as x2k summation n equals to 0 to n minus 1 x1m okay. Now this is simply DFT, endpoint DFT of x1n, that is equals to x1k. Okay, so this is the result. So we can say that x1n periodic convolution x2n has endpoint DFT equals to the product of the endpoint DFT of the signal. So this is the property that you can learn. Okay. So we have completed 8 properties. Now let's look at the ninth property, that is Parseval's theorem. Okay. So the Parseval's theorem states that if xn has n point DFT xk, okay, then summation n equals to 0 to n minus 1 xn whole square will be equal to 1 upon capital N summation xk mod square k going from 0 to n minus 1. Okay, so this is the thing. Now since this can be written as, so we will be proving it. Okay, so this is the theorem, we will be proving it. Since this can be written as n equals to 0 to n minus 1 xn multiplied by x conjugate n. Okay, now this is equation number 1. Okay, now if I replace xn by 1 upon n, okay, so this is the equation that we all know. So replacing xn in equation number 1 by equation number 2, we can get that so let me do some editing here. Okay, so we know that it is summation n equals to 0 to n minus 1 xn modes whole square. Okay, so this is the equation number 1. So in equation number 1, replacing xn by equation number 2, I can say that 0 to n minus 1 xn mod square will be equal to, there will be now two summations, n equal to 0 to n minus 1, 1 upon n is outside now, k equal to 0 to n minus 1 xk e to power plus j 2 pi by n nk multiplied by x conjugate n. So this is equation number 3. Now keeping all the terms having n as variable, so this is equal to 1 upon n okay. Now this, when you know that, we know that xk is equal to summation n equals to 0 to n minus 1 xn e to power minus j 2 pi by n n k. Okay, we know this. Now if we conjugate both sides, then there will be conjugate in left hand side, there will be conjugate here, and this will be a plus sign. So we can see that this whole equation, okay, so this whole equation is equal to x conjugate k. So we can say that summation n equals to 0 to n minus 1 xn mod square is actually equal to 1 upon n k equal to 0 to n minus 1 mod of xk whole square. Okay, so this we have proved it. So this is the Parseval's theorem. Proof can be used anyway if someone asks you, right? Now, so now let's look at another property, that is circular correlation. So The normal correlation, there's another video available on the channel, you can go through that for correlation. But circular correlation, as we know that suppose our xy tau, this is a simple correlation and we know the formula is x tau convolve y conjugate minus tau, or r xy m is equal to xm convolve y conjugate minus m. Okay, so this is the formula of the normal correlation. The circular correlation is rxym. The formula is summation, or I will write only the formula here. It is xm circular convolution of y conjugate minus m. Okay, so if I want to find the DFT of the circular convolution, so then it will be, we know that in case of circular convolution, the DFT is multiplication of the DFT of the individual signals, so it will be this. Okay, now since y conjugate m will have DFT as y conjugate minus k, so y conjugate minus m will have DFT y conjugate k. So this is the relationship that you can learn. So this I have proved it from the earlier properties. Okay, so this is the chart of all the properties that we have solved, and few more conclusions that I have already derived. So this finishes all the properties, and in next lecture we will be completing few very good examples of DFT. Okay, so thank you, and we'll be also solving the previous year questions of DFT. Okay, so thank you.